Welcome to this lesson on similar triangles. Before we begin the lesson, I'd like for you to work through these four warm-up problems to kind of summarize what we've been working on with ratios and proportions and the idea of similar figures. We'll use this information to help us in today's lesson. So if you would, please pause the video and work through these four problems, and then you'll have a chance to check yourself. Okay, and here are the answers to the warm-up questions. Okay. If you need more time, you can pause the video. Otherwise, we'll move on. This is our only postulate for today, and as it is a postulate, remember we cannot prove that this is true, but we will be assuming that this is true. We'll accept it as fact even though we can't prove it. Again, pause the video if you need more time. So we'll begin with this problem. We want to explain why these triangles are similar and then to write a similarity statement comparing them. Well, the only thing that we need to notice here is that we have vertical angles. So this angle here and this angle here are congruent. Given that, we have one set of angles, these two right angles at angle A and angle D, that are congruent between the two triangles, and we have angle BCA and angle ECD, these two vertical angles that are congruent. So between the two triangles we have two sets of congruent angles. Therefore those triangles would have to be would have to be similar by the angle-angle similarity. Now, in explaining why these two are similar, what we have to look at is that in one of the triangles, we have two right triangles. In one of them we have a 43-degree angle, and in the other we have a 47-degree angle. Well, remembering that triangles sum to 180, we already have here at angle B a 90-degree angle, which leaves 90 more degrees for the other two angles. If A is 43 degrees, that leaves 47 degrees for angle C. So that means that angle C has to be congruent to angle F. They're both 47 degrees. Since they're both 47 degrees and we already have the congruence of the right angles by our right angle congruence theorem, we can conclude that these two triangles are similar by the angle-angle similarity. The key here is that when you name the similarity statement, you've got to make sure you match up the right angles. So C was the 47 degree in the triangle on the left, and it's going to match with angle F in the triangle on the right. So we're going to have that triangle ABC is similar to triangle DEF. And you'll notice that how they're oriented, the right angles are on the first triangles on the left and on the second triangles on the right. So you have to be careful about making sure you're matching up the corresponding pieces. Obviously B and E go together. And so in our statement here, B is the middle letter for the triangle ABC, E is the middle letter for triangle DEF. But as we said, C and F had to match up as 47. So C is the third letter, F is the third letter. So we have those matching up. So triangle ABC is similar to triangle DEF by the angle-angle similarity. Okay, looking at this picture, we want to explain why triangle ABE is similar to triangle ACD, and then to find the length of CD, which is currently being represented by X. So what you have to notice here is that you have two triangles. You have triangle ABE, the smaller triangle, and then the larger triangle ACD. And we're comparing those two. So the first thing to realize is that what we have is angle A in both triangle ABE and in triangle ACD. So angle A is the same for both of them. And if you recall, whenever we say that an angle is congruent to itself, that is using the reflexive property. So to show this, we're going to use the reflexive property and the right angle congruence theorem to use our angle ABE that's a right angle and our angle ACD that's a right angle, saying they're congruent to each other between the two triangles, and angle A is congruent to itself between the two triangles. So we have two sets of congruent angles. that allows us to state that those two triangles are similar by the angle-angle similarity. Now the finding CD. Some of you might find it easier to rotate this picture 90 degrees clockwise in your mind. It would look like this, so that you're looking at the two triangles in more of a vertical sense. Now, what we have to do is make sure that we set up two ratios here and to a proportion so that we can solve for x. The common mistake in doing this problem is to say, okay, 9 here over 3 here, that must equal 5 over x. If you follow that proportion to its conclusion, what you're finding is you've got this 3 down here, and that's a third of the 9, so your x has to be a third of 5, so you would be saying that x is 1 2/3. Well, if x is 1 2/3, then how can it be longer in length than the 5? It can't. So don't go down that path. That is the most common mistake with a problem like this, is just going, okay, left side over this left piece equals this over this. The problem with that is you're supposed to be comparing two triangles. When you just look at this 3, you're only talking about this length right here, which is not the side of a triangle. In fact, it's the side of this trapezoid at the bottom. So what you need is the whole length from A to C, which is going to be a length of 12. By using that length, you'll actually get the correct answer. So we want to set up a proportion. So the idea here is that we're going to say CD, the x, over BE. So what we're doing is we're looking at the two bases of the two triangles, the big triangle and the little triangle. And we're going to set that equal to the whole left side of the big triangle over the whole left side of the smaller triangle. So we have CA over BA. Now, remember that your segment addition postulate tells us that CA is the same as CB plus BA, the two smaller segments combined. And that's what we're seeing over here, CB plus BA. So we've replaced the CA here with that statement. And that's just using the segment addition postulate. So we have our proportion. Now we just need to plug in our numbers. So replace CD with x, replace BE with 5, and then replace the CB plus BA with 3 plus 9 from here and here. And putting that over BA, we get 9. So what we have is our proportion set up. Now we'll change this to 12. 3 plus 9 is 12, and we use our cross product property. So we're going to say x times 9. So let's draw that real quick. We're going to say x times 9 equals, remember this is 12 now, 12 times 5, using our cross product property. And so x times 9 is 9x, and 5 times 12 is 60. So we have 9x equals 60. Using our division property of equality, we'll divide both sides by 9, and get that x is either 60/9 or 6 2/3, whether we want to leave it as an improper fraction or a mixed number. And that shows that x is bigger than 5, which makes sense when we look at the picture. Okay? So again, do not fall into the trap of just using this small piece in your proportion. You need to use the whole side for the big triangle. Alright, in this picture we want to explain why triangle RSV, again the smaller triangle, is similar to triangle RTU, the bigger triangle. We already have a set of congruent angles. We have angle RSV being congruent to angle RTU. But we also know that we can take angle R and set it congruent to itself, because R is an angle in both RSV and an angle in RTU, both triangles. So because that angle will be, and I should make that 2 arcs, because that angle is going to be congruent for both triangles, and this angle is congruent for both triangles, I have two sets of congruent angles, so the triangles are going to be similar by the angle-angle similarity. Now the trick is to find RT. RT, you'll notice, is the long side, and what we have is the length of the shorter side. So we want to set up our proportion. In order to do that, we will set up the equation that RT, this entire length here, over RS, the top piece here for the shorter triangle, is equal to TU, the base here of the large triangle, over SV, the base of the small triangle. The only thing here that's not a number is RT. So we'll just keep that as RT. You could call it X if you wanted to, if having RT in there messes you up, but it's just the thing that we're solving for. So by plugging these numbers in, I get RT over 10, just replacing RS with 10, equals TU, which is 12, over SV, which is 8. So now I can just do a little cross multiplying. It's also your choice if you want to simplify this ahead of time. So there's no requirement. You can just leave it 10 times 12 and RT times 8, or you could have made this 3 halves to shorten your work just a little bit. Okay? But RT times 8 equals 10 times 12. Then you have 8RT equaling 120. Dividing by 8 gives us 15 for RT. Now, if we look back at this, this should make sense. Looking at the base of the smaller triangle, I have 8, and looking at the base of the larger triangle, I have 12. Well, 8 is 2/3 of 12 because 4 goes into 8 twice, and 4 goes into 12 3 times. So there is a 2/3 ratio. 10 is 2/3 of 15 because 5 goes into 10 twice, and 5 goes into 15 3 times. So we could have looked at it that way as well. Now, this slide is just to give you a little bit of information on how the rules that we've been talking about all throughout this course about the reflexive property, the symmetric property, and the transit property that we had for equality and that we had for congruence also holds true for similarity. So there is a reflexive property of similarity that a triangle is similar to itself in that it would have a 1-to-1 ratio. The symmetric property of similarity, and all that's going to do is, if ABC, triangle ABC is similar to DEF, then it's also true that DEF is similar to ABC. The only thing that's going to change there is the similarity ratio. So for example, if ABC to DEF has a 1-to-3 ratio, then DEF being similar to ABC would have a 3-to-1 ratio. But they're still similar to each other, meaning that their corresponding angles are congruent and that the corresponding sides have the same similarity ratio. And then the transitive property of similarity, so that if you have 3 different triangles, if one triangle ABC is similar to triangle DEF, but DEF is also similar to a third triangle XYZ, then the first is similar to the third. ABC is similar to XYZ, and that's the transitive property of similarity. Okay, so we have reached the end of the lesson, and what I'm leaving here for you is a quiz question to have you explain why these triangles are similar and to find the lengths of BE and CD. That will be your extra credit question. So for watching the video, you have another extra credit opportunity. Make sure you don't tell your buddies because we'll be counting the hit counter to make sure that it matches up. But hope you have a great day and thank you for watching the lesson.